In this video, we're going to be looking at systems that are at equilibrium, and we've already seen a few examples of systems at equilibrium. We have looked at saturated solutions, and we've seen that there is a dynamic equilibrium occurring between the excess solute and it dissolving into solution. And so that's going back and forth, but since it's at equilibrium and saturated, the amounts of each don't change. We also saw an equilibrium system when we looked at the vapor pressure. As long as you had excess liquid in there, there's an equilibrium that exists between the liquid and the substance that exists as the vapor pressure, and how there's a back and forth there. In this slide and video, we'll also look at some examples of some chemical reactions, how there can be an equilibrium existing in a chemical reaction. Now, the type of chemical reactions that do this are called reversible reactions. Now, most reactions that we've looked at and done in our chemistry career have not been reversible reactions. Most of them have been reactions that they react, they do what's called go to completion, and then the reaction is over. For example, you may remember we had the little magnesium strip. We put it in the flame, it glowed real bright white, and when we were done, we had the white powder. The reaction started, it was over, it was done. There was no back and forth. So that is not a reversible reaction. Another one is when iron reacts and turns into rust. That is not a reversible reaction. Once your iron turns into rust, it's done. It's not iron anymore. I wish I could reverse it and get some of the rust back off of my car, but I can't. It's a once and done thing. But there are some reactions that are reversible, whereas when it goes and reacts to form products, sometimes those products actually react and turn back into the reactant to reform the reactants. And here's an example of one of those types here. And some of you may recognize this. If you've ever been to Friendly's, they have these types of straws where there's a chemical reaction going on inside, and under some conditions it's red, and then we can get the blue back, then we can get the red back. So we have this back and forth reversibility here between the red and the blue. So one reaction goes one way to make the red color, another reaction goes the other way to make the blue color. So that is an example of a reversible reaction. Looking at another example here. Here we have some N2O4. It decomposes into two NO2 molecules. So as this is happening, the NO2 molecules that we make, those actually can combine together and start making the N2O4. So we see this is just the exact same thing happening in the opposite direction. So it's called a reversible reaction. We have the forward reaction, the N2O4 breaking down into the 2NO2, but then that NO2 we're producing is going and it's making what we started with again. So we just have this big cycle that we're going through. So that's called the reverse reaction. Now, in chemical reactions, you have both of them are occurring at the same time. So as we're making the NO2, that NO2 is back reacting to get the N2O4. So they're occurring simultaneously. And now when we write a reversible reaction, we could write it as two separate reactions like we have done here, or we're always looking for shorter ways to do things. So a shorter way to write these is just to write that with a double arrow in between. And the double arrows kind of indicate that this reaction is occurring in both directions. So generally, we refer to the direction going from left to right. We refer to that as the forward direction. And then the right to left direction, that would be the reverse reaction or the reverse direction. So just looking pictorially here at what happens, here's our double arrow equation for this reaction. So notice we're starting off with just N2O4. That's all we have in the beaker to start with. So some of that's reacting and we're starting to make some NO2. But as we're making the NO2, some of the NO2 reacts and the reverse reaction kicks in to get the N2O4. So while we started with just the N2O4, when we're done, the reaction never really stops. It's just continuing the reaction. We have the forward and the reverse occurring simultaneously. So we've got this coexistence of both the N2O4 and the NO2. And some of the NO2 is changing into N2O4, but some of the N2O4 is breaking down into the NO2. And so this state of equilibrium. So this is very different than the reactions that react once and they stop and they're done. A reversible reaction is one where you just have this constant state of equilibrium. And of course, what makes it equilibrium is when they are occurring at the same rate. And at that point, our concentrations don't change anymore. Okay, to look at this graphically, here's an example of this same reaction graphically. So if I start off with all N2O4, obviously that is going to react and the amount of my N2O4 is going to get lower as some of it changes into NO2. And if I started with 0 NO2, obviously that amount is going to get up as some of the NO2 changes into it. So it's going to react, and as we go, the forward reaction is actually going to get slower. Notice it starts real fast when there's lots of N2O4, but as it goes on, my reaction slows down. Whereas the reverse reaction kind of does that as well. It's real fast. It kind of starts out slow, and then it scoops up fast, and then eventually everything levels out. And remember, when we reach equilibrium, equilibrium means that the amounts of each stay the same. So you can see in our graph here, at this point right here, everything is starting to level off. And so my amount of NO2 does not change from this point on. And my amount of N2O4 does not change. Even though there's still a reaction going, the N2O4 is still changing into NO2 and vice versa, my amounts have remained constant. And so that's when you reach equilibrium. So that's the meaning of equilibrium. Equilibrium does not mean you have equal amounts of both, because in this case here we actually have more NO2 than we do N2O4. But because at this point in time my concentrations are no longer changing, that is when we have reached equilibrium, and that's what we mean by equilibrium. So we can write some equations to help us understand and analyze what's going on at equilibrium. So remember, equilibrium is when the forward reaction and the reverse reaction are both happening at the same rate. And so when that happens, our amounts are no longer changing of each, even though the reaction is continuing. That's why it's called a dynamic equilibrium. So if we were to look and look at the amount of products that we have and compare it to the amount of reactions, we would have a ratio. And usually we do the concentration of, and it's usually written as the products over the reactants. And so we would have a ratio of what they were at equilibrium. And when we do that and calculate that and come up with actually the number, we call that ratio the equilibrium constant, which is abbreviated KEQ. And so really all that KEQ is it simply is the ratio of your concentration of products over the concentration of reactants. Now, in order for this to be the equilibrium constant, you have to put your concentrations at equilibrium in. Okay, you can't put your concentration of NO2 right here and your concentration of N2O4 in here, because if you put those amounts in, you're not at equilibrium right now. You're going to get a different ratio. So you have to wait until equilibrium is reached and then plug your concentrations in, and the ratio of the two is what's called the equilibrium constant. Okay. Now that particular ratio that we get is only good for that reaction, and it's also only good at that particular temperature. If you think back to the activity we did in class with our water vapor and where we were moving from one side of the room to the other, okay, I think we reached equilibrium. I think we had 6 people existing as water vapor and 4 people existing as liquid. That was our equilibrium that we established. So we had a 6-to-4 ratio at that point in time. Well, if we raised the temperature and did it at a higher temperature, we would have more existing as water vapor. So we'd maybe have 8 people as water vapor and 2 people. So we'd have a different ratio. Okay, so your KEQ values are only good for that particular reaction at that particular temperature. So to generalize a reversible reaction, here's just a generic reversible reaction where we have substance A reacting with B to make C and D. If we were to write the equilibrium expression for this reaction, well, remember, it's the ratio of your products, so that's our C and D, over the reactants, which are our A's and B's. Now we set this up to say that that's equal to KEQ. Now you'll notice in this example here it's called KC. In this case they're using the C for constant. Remember, it's called the equilibrium constant. And so you might see it written as KEQ, or you might see it written as KC. They both mean exactly the same thing, so they are interchangeable. So don't let that confuse you. Again, we've seen square brackets a time or two, but remember, whenever you see the square brackets around something, that stands for concentration. So my products are C and D, and so my ratio is the concentration of my products, and note that they are multiplied times each other, divided by the concentration of my reactants. Now you'll also notice that these little lower letters would represent coefficients in an equation. And so whatever the coefficient is in your balanced equation for the reaction, that actually becomes your superscript when you write your equilibrium expression. Okay, so this whole thing that we have here is what's referred to as the equilibrium expression. You have your equilibrium constant, or the KEQ, and then here's your concentrations of things. So if we have a balanced equation for the reaction, we can always write the equilibrium expression. For example, let's look at our equation that we've been looking at, and we want to know, well, what is the equilibrium expression for this reaction? Well, it's simply the ratio of our product concentration over the reactants. So our product is NO2. So we have our concentration of NO2 here, and since my coefficient in front of it is a 2, then I make that squared. Okay, and it's my products over the reactants. Well, my reactants are N2O4, and again, I put the square brackets around to represent concentration, and there's no coefficient written in front of that one, so it's just to the first power, which of course I don't need to write. Now, we said that our ratio will be different if we have different temperatures. But what if we have different concentrations? What if I started with different amounts? How would that affect my ratio? Okay, so we're going to take a closer look at this reaction where our colorless N2O4 gas reacts and breaks down to make brown NO2 gas, but it's a reversible reaction, so as we're making the NO2, it reacts to make more N2O4. So we have this back and forth. So looking at our equilibrium expression, we have the ratio of our products, which in this case is the NO2. Again, remember the brackets mean concentration, and divided by the N2O4. So if we were to write an equilibrium expression for this, our KEQ, and there should be either an EQ or a C down here, would be the NO2 squared, and notice again that this 2 up here comes from the coefficient. And that's where we get that. Whatever coefficient you have out in front, that's what your superscript is. So our N2O4 had nothing, so there's just a 1 there. So for this particular reaction, we have an equilibrium of about 4.63 times 10 to the negative third. That is the ratio when that thing is at equilibrium. Now let's see what happens, what kind of ratio we get. Does it depend on what we start with? So let's do our first example. If we were starting with just N2O4, we're concentrated N2O4, there's nothing else there. So here's our picture here. It's the colorless gas, so we see that's colorless here. And you see all of our molecules in there are all N2O4 molecules. And when we let that react, notice that they start breaking down. And so we start getting some NO2s, but then as we make NO2s, they come back together to make N2O4 again. So we just have this constant back and forth. Eventually, the breaking apart and the putting together will start occurring at the same rate. And at that point in time, we will have equilibrium. And once we reach equilibrium, our concentrations don't change anymore. So notice the N2O4 concentration got less originally, and our NO2 got bigger originally, but then we got a point where they equaled out. So our concentrations at equilibrium were 0.643 and 0.0547, and when we pop those values into our equilibrium expression, we get a ratio of 4.65 times 10 to the negative third. So that's our ratio if we started with pure N2O4 and no NO2. So let's try this a different time, this time starting with only NO2, which is our brownish gas. And so we can see that the NO2 is combining to make N2O4, but then some of those N2O4s are then breaking apart to make more NO2. Eventually, the forward and reverse will be occurring at the same rate. When that happens, we will reach equilibrium. And so you can see our concentrations will be leveling out once equilibrium is reached, where they are no longer changing. And so at equilibrium, you see our N2O4 concentrations, 0.0898. Our NO2 concentration is 0.0204. So if we pop those values into our equilibrium expression, we come up with a very similar answer. Again, we get 4.63 times 10 to the negative third. We get the same ratio as we did as if we had started with N2O4. So it didn't matter what we started with. When we reach equilibrium, we still got the same ratio. Let's look at one last example. This time we're going to start with a mix of both. So you can see we've got some brownish in here as well as some other gas. And so we'll let that start reacting. And so our amounts of each are going to change. So you can see that the N2O4 is breaking down. We're actually, we started with a lot of that, and that amount is getting less and less. And the amount of NO2 that we start with, well, that amount is increasing. Eventually, we're going to reach equilibrium, where those concentrations won't change anymore. And so here's our values. The N2O4 is 0.491. The NO2 is 0.0475. If we pop those into our equilibrium expression, we get, again, just about the same ratio, 4.60 times 10 to the negative third. So we see that it did not matter what we started with. As long as we had the same reaction occurring at the same temperature, we always got the same value for KEQ, in this case about 4.6 times 10 to the negative third. So as we just saw, the ratio, the equilibrium constant, does not depend on the initial concentration. And here we see data from 4 different experiments, and you can see they started with different concentrations of each reaction each time, and we still got the same ratio. So in our first example, we had 0 N2O4 and a concentration of 0.02 NO2, and we got a ratio of 0.211. Trial number 2, they changed the concentration of the NO2 to 0.03. We still got the same equilibrium constant. And you can see the other 2 trials, we changed the initial concentrations, and we're still getting the same ratio. Now notice that the concentrations are different, but when we pop them into the expression, the ratio is still the same. So again, your equilibrium constant does not depend on the initial concentration. It is always the same for that particular reaction at that particular temperature. Now when you're writing equilibrium expressions, we always include the concentration in there. And if you're working with gases or if you're working with solutions, we can talk about concentration. But what if we have things that are solids or liquids where the concentration is not really applicable there? The concentration doesn't change. Well, good news here. When you're writing an equilibrium expression for an equation that involves solids or liquids, since their concentration does not change, you actually just totally leave them out of your equilibrium expression. So here you can see the lead chloride is dissolving in water into our lead and chloride ions. So when we write our equilibrium expression, we have our concentration of the products, which are the lead and the chloride. Again, since the coefficient is 2, you have a subscript of 2 for the chloride. And we put this over the reactants. Now in this case, the only reactant is lead chloride, which is a solid, so we just leave it out of the expression. If you want to, you can put over 1 or just write it as is. So if we were doing the calcium carbonate breaking down, same thing here. We would have products, our reactants, we would just leave out the calcium carbonate because it is solid. So it does not affect the equilibrium. As long as there is some of the solid and liquid present, the reaction will continue, the reaction will be at equilibrium. So now it's your turn. Here we have an equation for a reaction of phosphorus reacting with chlorine, making our phosphorus trichloride. So look very carefully here and let's see how well you paid attention and write your correct equilibrium expression. So KEQ would equal which of the following? So pause the video now and write down your answer. Okay, hopefully you have your answer written down, and if you were paying attention, you should have chosen answer number 3. Looks a little weird, but it's always the products over the reactants. In this case, our products are PCl3, but they are liquid, and we don't include liquids when we write the equilibrium expression. So we just have a 1 for our products. Our reactants, well, the phosphorus is solid, so that's not included, and the chloride is a gas, which that is included. Again, a coefficient of 6, means that we should have a 6 up above as the superscript. So let's try a few more. Here's 3 examples. So pause the video right now. You have these examples on your sheet. Go ahead and write the equilibrium expression for all 3 of these guys. And remember, the expression is a complete equation. So make sure you write KEQ equals and then write the other side. So pause it now and play it when you have these all done. Okay, let's take a look at the first one. If you did a good job, you should have this expression written here. Again, it's always products over the reactants. In this case, the tin is a solid, so he does not get included. We have our carbon dioxide, coefficient of 2, so you should have a 2 as a superscript. Also make sure that you have the square brackets written in. Remember, that stands for concentration, and when we actually get numbers for concentration, we'll have to pop that in. Okay, so we have our products over the reactants. Again, the tin compound here is a solid, which does not get included, and so all we have is our carbon monoxide squared. For the second example, very similar. In this case, everyone is a solid except for our one carbon dioxide product, and actually there's no coefficient there, so ignore this 2. That 2 should not be there. It's just Kc equals CO2. Do make sure that you have the CO2 in brackets and get rid of that 2. Last example, we have our zinc and copper reacting. Good old single replacement reaction here. In this case, the zinc is solid as well as the copper products. So when we have our products over reactants, we just have the zinc ion listed. Again, make sure you have it in brackets. We need the concentration of the zinc ion. We leave out the copper. Over the reactants, since the zinc is solid, that does not get included, but the copper ion does. So hopefully writing these is pretty easy. Just pay attention to your states. It is very important to include who's solids, who's liquids. Finally, let's look at an example where we actually have some numbers. So here we have a reversible reaction with hydrogen and iodine. So there's our balanced equation. So pause the video now and write your equilibrium expression for this reaction. Alright, so let's check to make sure you have that written correctly. You should have KEQ or KC equals, you should have, again, make sure you have the square brackets. It's our products, which is HI, coefficient is 2, so they're squared, divided by the reactants. None of these are solids or liquids, so everything gets included in the expression. And so again, make sure you have your square brackets, so it's divided by the concentration of hydrogen times the concentration of the iodine. Now in this case we actually have numbers, so we can plug those into our equation. And so our hydrogen iodide concentration is 0.788 molar, and notice that is squared, so when you punch that into your calculator, a common mistake is to forget to square it, so please be on the lookout, don't forget that. And then our 2 concentrations are 0.106 molar on the bottom, so we punch that into our calculator and we should get a final answer that our ratio or our equilibrium expression is 55.3. Notice there are no units on that answer because we have molar squared on top divided by molar squared on the bottom. They cancel out. So a lot of times you will not have a unit for your KEQ value, but sometimes you do. It just depends on the situation. So do your dimensional analysis to make sure you have the correct unit on your answer. Now tomorrow in class we'll take a look at what this means. If our ratio is 55.3, what does that mean? Why do we bother doing all this? Okay, but hopefully now you know how to write expressions correctly and actually calculate values if you are given the equilibrium concentrations.